Good morning, good afternoon, or good evening, my friends. I hope you are doing well today. Today we are going to jump into lesson 8.5, which is all about electric circuits. But before we do that, if you have not yet looked at lesson 8.4, which is about Ohm's law, I strongly encourage you to go back and check up on that first, because we are going to be using Ohm's law to solve some skill practice questions in today's lessons. All right, let's jump right into it. So first of all, what is a circuit? Well, in terms of electricity, a circuit is a closed conducting pathway. Now, we represent circuits using circuit diagrams, and this is just sort of a stylized circuit diagram that I made in PowerPoint. If you look at real-life circuit diagrams, they're much more complicated than this with many, many more symbols all spread around. So we're going to be using just some very simplified type circuit diagrams. This little symbol here represents a DC power supply. DC stands for direct current, which indicates that it pushes electric current in one direction only. The opposite of DC would be AC, which is alternating current, and that's what you get when you plug something into the wall, which causes the electric current to wiggle back and forth 60 times per second in the United States. But we're going to focus mainly on just DC, so this is like a battery. In a circuit diagram, the current, the direction of the current is conventionally coming out of the positive end of the DC, which is represented by the longer line, going around the circuit and then returning into the DC power supply through the shorter end. In real life, electrons come out of the negative end of the battery and go around the circuit and return to the positive end. So it's just sort of a thing you have to remember, that when we're talking about the conventional direction of electric current, it always flows from positive to negative. But in real life, electrons flow from negative to positive. It doesn't really make any difference. The math still works out. It's just a little quirk about the way we draw circuit diagrams. Now, in a series circuit, all of the resistors lie in one pathway with the power source, so that when the current leaves the power source, it must flow through all three resistors in turn before returning back to the power source. I say three resistors, it could be 2 or 5 or 20, but they're all in a single line. Old-timey Christmas lights are wired in series, which is why when one of the bulbs goes bad, it causes the entire strand to go out, because if there's a break in the circuit, then none of the other bulbs can receive electric current either. In a series circuit, the current flowing across all of the resistors is the same. So for example, if there's 1 amp of current flowing across this resistor, then there's 1 amp flowing across this resistor and this resistor as well. The potential difference across each resistance is directly proportional to the magnitude of the resistance. So the bigger the resistor, the greater the potential difference across that resistor, but the current is the same regardless. When we're looking at a series circuit, we can imagine collapsing all of the resistors in series into a single equivalent resistor. And the equivalent resistance is equal to the sum of the individual resistances. So to show you what I mean, imagine you have a circuit with a 30-volt power supply and 3 resistors wired in series of 30 ohms, 20 ohms, and 10 ohms. This is equivalent to a circuit with a single resistor of 60 ohms. 60 is equal to 10 plus 20 plus 30. So the current flowing through this single 60 ohm resistor will be exactly the same as the current flowing through these 3 individual resistors. And to find what that current is, we can use Ohm's law. Current is equal to voltage divided by resistance. The voltage supply is 30 volts and the equivalent resistance is 60 ohms. So we take 30 volts divided by 60 ohms, and that gives us half an amp, 0.5 amperes. So when we spread that back out, each of these resistors has half of an amp flowing through them. As half of an amp of current leaves the battery or the power supply, flows through all 3 resistors, and then returns to the power supply. Because there's no other pathways for current to flow, every single ampere that leaves the battery must flow through all 3 resistors, or in this case, half an ampere. Now, we want to calculate the voltage, or the potential difference across all 3 resistors. Rearranging Ohm's law a bit, we get voltage is equal to current times resistance. So for this first resistor, the current is 0.5 amps and the resistance is 30 ohms. 0.5 times 30 is 15 volts. So as the electric current flows across this first resistor, there will be a potential difference of 15 volts. For the second one, it's 0.5 amps times 20 ohms, which is 10 volts of potential difference. And for the third, it's 0.5 amps times 10 ohms, which is 5 volts. If we add these three potential differences together, we should get the same as the total potential difference for the battery. And that's because each charge that leaves the battery must lose 30 volts of potential difference before it returns to the battery and gets charged up again. So let's take a look at our first skill practice question. We have a circuit diagram and we are being asked to calculate the current and potential difference across both of the resistors in this circuit. So I've moved it to the new page to give myself a little bit more space to work, and I am going to label these resistors. I'll call this resistor A and I will call this one resistor B, so that when I'm solving these equations over here, you'll know which resistor I'm referring to. Now the first thing I'm going to do, because these two resistors are in series, I'm going to collapse them down into a single equivalent resistor. So I'll very crudely draw my power source. Here's my resistor. The power source is 24 volts, and my equivalent resistor is equal to 5 plus 3 ohms, which is 8 ohms. So these two circuits are equivalent. So now I'll work out the current in my equivalent circuit, and that will then give me the current across both of the resistors. I is equal to V divided by R. That's Ohm's law. The voltage is 24 volts, and the resistance, the equivalent resistance, is 8 ohms. 24 divided by 8 is 3 amperes. So the current across this equivalent resistance is 3 amperes, which means that the current across this resistor is 3 amperes and the current across this resistor is 3 amperes, because remember, the current is the same across all of the resistors as long as they're in series. Now we will work out the voltage or potential difference across each resistor. So the voltage or potential difference across resistor A is equal to the current across A multiplied by the resistance of A. The current across A we've already determined is 3 amperes, and the resistance of A is 3 ohms. 3 times 3 is 9. So the potential difference across resistor A is 9 volts. Now let's do the same thing for resistor B. The current across resistor B is still 3 amps because it's in series with A, but the resistance of B is 5 ohms. 3 times 5 is 15 volts. So there's a potential difference of 15 volts across resistor B. We can check our work by adding up the voltage across resistor A and resistor B, and if we've done everything correctly, it should add up to the total voltage of the battery, and it does. 9 plus 15 is equal to 24, so that's just a good indicator that we've done everything correctly and got the answer we were supposed to get. Next, let's talk about a parallel circuit. In a parallel circuit, there are multiple branches or multiple pathways that the current can flow through. So when a charge leaves the battery, it can reaches this junction, it can either turn and go through this pathway, or it can continue on, where it can turn and go through this pathway, or it can continue and go through this pathway, and then will eventually return to the battery. Now, each charge only chooses one pathway before returning to the battery, so it's not like it can go down one pathway and then double back to go down the other pathway. There's a definite flow of current, and each charge has to follow that flow, and it chooses one pathway or another to go down. Now, in a parallel circuit, the potential difference across each branch is going to be the same. So if you know the potential difference of the battery, that's the same as the potential difference for each branch. However, the current across each branch will be inversely proportional to the total resistance of that branch. So let's see how that would work. Imagine we have a parallel circuit with 12 volts of electric potential, and on one branch we have a 6 ohm resistor, on another branch a 3 ohm resistor, and on the last branch a 2 ohm resistor. The potential difference across each branch is going to be equal to the voltage of the battery, because each charge that travels down, say, this branch has to lose 12 volts worth of potential difference before it returns to the battery to get charged up again. And the same is true for each charge that comes down this branch and each charge that comes down this branch. Now we'll use Ohm's law, I is equal to V divided by R, in order to determine the current across each branch. So for the first branch, the voltage is 12 volts and the resistance is 6 ohms. 12 divided by 6 is 2 amperes. For the second one, the voltage is 12 and the resistance is 3. 12 divided by 3 is 4 amperes. And in the final branch, we have 12 volts divided by 2 ohms, so the current is 6 amperes. If you've ever heard the expression that electricity follows the path of least resistance, this is pretty much what it means. The current across each branch is inversely proportional to the resistance on that branch. So the strongest current travels through the branch with the least overall resistance, and the weakest current travels through the branch with the greatest resistance. So here's our next skill practice question. Once again, we're being asked to solve for the current and potential difference across each resistor in this circuit. So once again, I will start by labeling my resistors. I will call my 4 ohm resistor, resistor A, my 10 ohm resistor, resistor B, and my 5 ohm resistor, resistor C. Now it is not necessary to collapse this circuit into an equivalent resistor. We could, but the math is a little bit more complicated. You don't just add them together. But it's not necessary to do that anyway, because the potential difference across each branch is going to be the same, or 20 volts. So there'll be 20 volts across this branch, 20 volts across this branch, and 20 volts across this branch. And now we just have to use Ohm's law 3 times to work out the current across each branch. So the current across branch A will be equal to the voltage across the branch divided by the resistor A. And the voltage, of course, is 20 volts because it's the same across all branches. The resistance on branch A is 4 ohms. 20 divided by 4 is 5 amperes. So there will be 5 amps of electric current flowing across this first branch. Now let's take a look at the second branch. The current across branch B is equal to the voltage divided by resistance B. The voltage is 20 volts, of course, and the resistance on branch B is 10 ohms. 20 divided by 10 is 2 amperes. So there are 2 amps of current flowing across branch B. And finally, let's find the current across branch C. Take the voltage divided by resistance C. The voltage is 20 volts, and the resistance on branch C is 5 ohms. 20 divided by 5 is 4 amperes. We add that together. Well, excuse me, we don't have to add it together, but if you did add it together, you would find that the total current flowing through the battery must be 5 plus 2 plus 4, which is 11 amps. That's not something we have to find out to solve the problem, but it's just a piece of information that you can work out if you wanted to. Let's take a look at one more skill practice question. This circuit has elements of both series and parallel circuits, so let's see what we can do with it. As always, I'll start by labeling the resistors. So we'll call this one resistor A, resistor B, resistor C, and resistor D. Just makes things easier to refer to them later. Now, because we have some resistors in series, we'll start by partially collapsing this circuit down into something a little bit simpler. So I'll draw my power supply. I'm still going to have 2 branches, but each branch will only have 1 resistor on it instead of 2. So on the first branch, the equivalent resistance will be equal to the sum of resistor A and resistor B, which is 6 plus 10, that's 16 ohms. Easy enough. And on the second branch, the equivalent resistance will be equal to 16 plus 8, which is 24 ohms. Now, we know that the voltage across each branch, or the potential difference across each branch, is going to be 48 volts. So we can use that information and Ohm's law to determine what the current across each branch will be. Across the first branch, the current will be equal to V divided by R, which is 48 volts divided by 16 ohms. 48 divided by 16 is 3 amps. So the current across this first branch will be 3 amperes. And on the second branch, the current will be equal to 48 volts divided by 24 ohms. 48 divided by 24 is 2 amperes. So the current across the second branch is 2 amperes. Now when we go back out to our initial circuit, remember these two resistors are in series, so the current across them is the same. So if the current across this branch is 3 amperes, then the current across this resistor is 3 amperes, and the current across this resistor is 3 amperes. Likewise on the second branch, if the current across this branch is 2 amperes, then that's what the current is across both resistors. We can just kind of take that information and spread it back out. Now we have everything we need to work out the potential difference across each individual resistor. So we'll start with resistor A. The potential difference across resistor A is equal to the current across resistor A multiplied by the resistance. The current across resistor A is 3 ohms. 3 amperes. We already figured that out. And the resistance of A is 6 ohms. 3 times 6 is 18 volts. So the potential difference across resistor A is going to be 18 volts, Now let's move to resistor B. The voltage across resistor B is equal to the current times resistance B. Well, the current across resistor B is still 3 amperes because it is in series with resistor A, but the resistance of B is 10 ohms. 3 times 10 is 30 volts. So the potential difference across resistor B is 30 volts. And if we add 30 and 18, we get a total of 48, which that checks out because every charge that travels down this branch must lose a total potential difference of 48 volts before returning to the battery. Now let's work out the voltage for resistors C and D. The current across resistor C is 2 amperes, and the value of resistor C is 8 ohms, and 2 times 8 is 16 volts. And finally, the voltage across D is equal to 2 amperes multiplied by 16 ohms. And 2 times 16 is 32. And again, we can stop and do a little bit of a reality check. The total voltage or the total potential difference across this branch must be equal to 48 volts. And it is. 16 plus 32 is equal to 48. So that checks out. And folks, that is going to be the end of lesson 8.5. I appreciate your time and attention. Please hop on over to Google Classroom. I'll have an assignment there for you related to lesson 8.5. Please join me tomorrow when we will be in lesson 8.6, which is about electrical power and energy. It ought to be a pretty short lesson, especially compared to today's lesson. Thank you for your time and attention. Take care of yourself. As always, keep washing your hands. I will talk to you tomorrow. Bye.